Hi, I'm Sean Prestridge, U.S. Field Applications Engineering Team Leader for IAR Systems, and I'm going to be your guide through this video on how to isolate defects quickly. What we're going to talk about are some of the more common defects that developers encounter inside of their code when they're doing debugging. In other words, runtime or dynamic analysis. And then we're going to look at what options you have to help you find these defects a little bit more quickly. And finally, I'll finish up with a quick demonstration of how we solved that problem at IAR Systems. So the most common defects that developers run into are arithmetic problems, such as integer overflow, underflow, shift overflows. Actually, divide by zero is a huge problem because in many of the example applications that we see that come from silicon vendors, they typically have the divide by zero trap vector turned off. So if you perform a divide by zero, it actually just returns zero and you have no idea that you just performed an illegal operation. Also, unhandled cases and switch statements where people don't provide a default statement because they think they've handled every single thing that could come across that switch statement, and then through the course of debugging they find out that they really haven't. Also, bounds checking is a huge problem. Oftentimes when we're dealing with arrays, we work with computations of the index of the array, and what we find is that sometimes our computations go awry and we wind up accessing the variable or that array outside of its bounds. Or if we're using a pointer off the heap, perhaps we go beyond the end of the pointer. So that's another huge source of problem where we accidentally corrupt the global memory space. Also, if we're using heap, we may run out of heap space and we're not malloking things properly, where we're actually checking the return values from the malloc. We might be freeing pointers twice accidentally inside of our source code. So there's many sources of errors inside of the heap. So if we look at integer overflow, that's a case where as we are performing some sort of calculation, we actually overflow what could be, for example, the 32-bit value maximum integer if we're on a 32-bit microcontroller. Additionally, integer conversion failures are another huge source of problems where we're either doing an implicit or explicit cast and it materially changes the value of how that variable is interpreted. So this can oftentimes cause a problem, particularly when you're doing an implicit cast to or from a signed to unsigned quantity or vice versa. So what can happen is that you may not be cognizant of the fact that you're doing an implicit cast, and so you get an unexpected interpretation of what that variable is. Also, shift overflow and underflow. Oftentimes shift is used because it's a very easy way to multiply by 2 or divide by 2. So if you don't have a floating point unit on your microcontroller, it's a quick way to do some floating point or some mathematical operations on your number that you may be working with. But sometimes you accidentally flow beyond the end of the register that you have. So in the case of a 32-bit register, if you flow beyond that, that might be a source of a problem, or it could be something that you intended. But it is a very common issue that developers run into, so this is something that we need to be aware of. I mentioned the problems with division by zero where you don't have that trap vector turned on, so you definitely want to watch out for this sort of thing. The unhandled switch case, again, we oftentimes will see folks that think they've handled every single case that could come through a switch statement, and then they get surprised during their debugging that they actually didn't. Heap errors oftentimes are a common source of errors because people have cases where they're mallocing data off the heap. They think they have enough heap space left, but the heap has become very fragmented because of their allocation and deallocation of memory off the heap. So they may have enough memory left in the heap, but they don't have enough contiguous memory left in order to be able to malloc off some other pointer that they need. So it's a very common source of errors. And we talked about the out of bounds access, where you accidentally compute an index that's beyond the end of an array or a pointer. So this can corrupt the global address space and lead to wild pointers, or perhaps the code going off into the weeds. So this is another big source of issues that developers typically run into. So what options do you have to detect these kinds of things? Well, if you look at the build tools, the compiler and linker can sometimes give you some contextual clues that there's something amiss. Typically, we like to say that warnings are errors waiting to bite you, so that you should always clean up your code so that it compiles with 0 errors and 0 warnings. But the compiler and linker don't do very thorough checks of what your code is. It just looks more for syntactical issues and very obvious problems inside of your code, but it doesn't really do the deep analysis. So some of the things that you can do inside of your code, you can use asserts to try to prove out whether or not something that you believe to be true is actually the case in your code. Closely related to that, you can also manually instrument your code looking for erroneous conditions, such as every time you do a divide or a division operation, you can check the divisor to make sure that it's not actually 0. Now, these do work, but it requires that the onus is on you to put all of this inside of your code and to remember to take that out in the actual code that you're going to deliver at production time. And of course, we always run out of time, and so we wind up leaving some things inside of the code because we don't want to modify it from what we've actually done extensive testing. So this can cause a little bit of problem. Another way that you can get around it too is by using automated code instrumentation methods. In other words, something that does dynamic or runtime analysis of your source code. So if you look at that chart that we had a minute ago where the compiler and linker can catch some issues, if you use that in conjunction with runtime analysis, and especially if you also use static analysis with runtime analysis, it can help find many more types of defects. So with that, let's go to a quick demonstration and we'll see what this looks like in real life. So here we have an example application, and we at IAR Systems have a tool called crun that can do this type of runtime analysis. And to enable crun, you just go into your project and into options, and you go to runtime checking and you enable this, and you can see that we have the ability to do checked heaps, bounds checking. All the things that we just talked about are common sources of errors. So if you want to see what this looks like in source code, we can just build our project and then download to the target, and we can see what it looks like when we're running. So once the application starts up, one of the things that we have are crun messages, and so if we run our code, you can see that we very quickly hit a divide by 0. Now in this particular case, you can see that we get a full call stack that shows us how we got to this particular divide by 0. So in certain cases it may be a little bit difficult to figure out how did I get to this particular point in code. By having that call stack, it makes it a little bit easier to figure out how things got to that particular point. But something else to point out too is that in the disassembly, it does the check to see if the divisor is 0 before it actually performs the division. So in other words, before it performs the bad action. So this is particularly important when you do things like an access out of bounds on an array or a pointer. So it can halt the core before you start clobbering the global memory space. So if we continue on, you can see that there's an unhandled case in the switch statement, so you can very easily check why did I not have that particular case covered. Again, it gives you the full path through the code, so it makes it very easy for you to figure out how you got to that particular point. Here's a case where we have a shift overflow. Maybe this was what we intended, so what we can do if we determine that this is okay, we can right click on this violation and we can add a rule for this specific violation at this line of code, or for the entire piece of source, or for the entire project if we wanted to. And those rules will give us the opportunity to either ignore that warning or to just log it and not halt the core and just keep moving on. So by using this type of analysis while you're desk checking your code, it can help you find these types of defects before you put it into a formal build. Because once you put it into a formal build, then every defect counts against your release metrics. And so using this type of code analysis can help you get your code out into the field faster, because you can meet your release metrics much more quickly. Thank you for watching this video.